Hello, can you hear me?
Yes,
Yes, sir.
sir.
Yes, sir.
Okay. Okay. So I should share the slides. Let me. Can you see the slides?
Yes, sir.
Can I start?
Sure, sir. We are
Okay.
starting.
So good afternoon
So,
to all. We again back to the second part of this talk. The second part of the talk will, in fact, cover what is written in the title of the presentation at the beginning. So, we are talking about the spectrum issues. We are talking about the energy efficiency issues. Of course, there were security aspects. So these three we touch upon in previous talks, particularly cognitive radio as a means of opportunistic communication for the secondary data communication over the primary user spectrum was discussed. We also see that, well, cognitive concept by means of spectrum sharing, it may be under interwaves, or it may be underlay, or it may be overlay mode of spectral access or spectral sharing, can address the spectral information. But there is, of course, the issues. The issue is the power issue or the energy issue, because the devices, IoT devices, are battery limited devices, and if they like to transmit their data using the carrier signal, separate carrier signal like the traditional communications, then we have to take help of power. I mean, we have to face the use of power hungry RF circuits, RF oscillators, and converters. These are very, very power costly as well as power consuming. So, active data mode of communication or traditional radio wave communication may not be pertinent for IoT communication. So, to start with these discussions, we understand that with the emergence of IoT, there will be 150 billions of wireless devices or nodes expect to come in 2030. So it needs a seamless connectivity. If dedicated channels are to allocate, then we need 76 gigahertz spectrum. What I'm going to say, that this 130 millions of, sorry, billions of nodes, if they connect among themselves for data communications, and if we provide exclusive channel bandwidth, so we need to provide at least 76 gigahertz spectrum. On the other hand, if cognitive radio concept is used, the spectrum allocation goes down to 19 gigahertz. So one-fourth reduction. It may address to an extreme the spectrum related issues. But the question again, the power, as I already say at this beginning, that if the IoT device has to use its own radio wave carrier communication, I mean a traditional mode of digital communication for data communication, then it has to has it has to use the carrier wave generator, that means RF source, RF circuit processing, baseband circuit processing, converter, oscillator, amplifier. These are not only costly but also it is power consuming or power hungry. Its deployment is really, really infeasible. It's very costly. To overcome these issues, the concept of backscattered communication, which we call as symbiotic radio communication, which we call as a cognitive backscattered communication, is introduced. Go back to our school day biology class. We know symbiosis, that is nitrogen fixation, uh, ribosomes, rhizobiums, and which helps in the host plants for the fixation of the nitrogen. So it's a kind of mutualism. Of course, this cooperation, win-win game may not be always. It would be mutualism. It may be competitive. So two entity in biological systems collide, coupled together, where benefits of one is achieved, obtained from the others. So same concept is used in IoT communications. This is symbiotic radio. By symbiotic radio, before I come, let us go to the backscattered communication. What is backscattered communication? So this is a backscattered transmitter. So backscattered communication consists of two parts. One is RF source or the signal source. So this signal source is basically the RF carrier wave source. So there exist RF carrier waves, and this is the backscattered transmitter which contains one or two antenna, and this is the backscattered receiver. Now, this is IoT device. There are say smart devices that captures data, IoT devices, which we call at the IoT devices or parasites device or smart device which captures data. Now this data needs to transmit to the backscatter receiver, but it will not use of its own carrier signal. Rather, whatever existing carrier signals are there, these carrier signals impinge on the antenna or this, and by changing the load of this backscatter device, the reflection coefficients get changed. So, or in other sense, the impinged radio waves retransmit or remodulate and go back to the backscatter receiver. So what it is other way like to say is that this backscatter transmitter doesn't use of its own radio wave as carrier signal. Instead, it makes use of the carrier signal. These carrier signals coming from the other signal source, incidence on this, and the backscatter device or the transmitter or IoT device, whatever data it captures, put on this data onto the incident RF waves, and these signals remodulate or retransmit to the backscatter devices. So there is win-win game. Why I am calling this win-win game? Uh, the signal, this source, let's say this is a primary communication. This is right. So there is uh, one direct path and one is the reflected wave path. So IoT passive devices. Let us come to the this communication concept in the context of other cases. So there are two ways this backscattered communication can be done. One is here it is the existing signal source, that is only the RF source or the oscillator circuits that generates the sinusoidal carrier waves that can be used as the carrier, or it can be of existing other RF sources like Wi-Fi communication or cellular communication. So it could be thought of like a primary communication. Now this primary communication, if this were not there, let's say this reflected wave path were not there, then what would happen? The primary signal goes to the receiver signals, but which is here the backscatter receiver. So let us assume that there is a single receiver, and this receiver is the primary receiver. So this signal source may be wireless signals like Wi-Fi communication, or it can be cellular communication. So we call it as a primary communication. So a concept of cognitive radio, like say primary communication, and this is the primary receiver. This direct path may be weak signal, so the primary communication is not up to the mark. On the other hand, the IoT device or backscatter device, these are passive device, battery limited operations. They don't like to use the RF circuits. They don't like to use of its own RF carrier. Instead, their signals or their data rather to be impinged on the incident RF wave of the primary communications and retransmit or remodulate to the devices. So this devices receiver, I call it as a common device for primary as well as your IoT device or secondary communication. So there are win-win game. In what sense? The primary communications now getting two paths. One is the direct path, which seems to be weak signals, but by means of this reflected signal, it would have a indirect path of communication. So primary communications are now being improved by means of direct path communication as well as the reflected path communication. On the other hand, the IoT device, the passive devices, passive communication, accomplished RF communications of primary users carrier signal. It need not have to use of its own carrier signals. It doesn't need to use of its RF circuits. So it can save power, and at the same time it make use of the carrier signal of the primary user or primary communication. So it's neither use the primary communicate. I mean, it's neither use the carriers or the spectrum. So it's spectrally efficient as well as it does not use the energy consume or energy cost. I mean, costly and energy consume RF circuitry. So this is the benefits that secondary is getting, and at the same time it provides a reflected path, which is the extra path or a diversity for the primary communication. So primary is also getting a benefit. You know that there are kind of, actually this what I'm talking here, it is basically one mode of symbiotic radio communication. One mode means this mode is basically your bi-state or monostate. For example, in RFID, you might know the radio frequency identifier. What is basically in RFID does, or that say this is a generated source. If it is an RFID detector, and if it is a cell phone line, so what is exactly done? This carrier signal in RFID, this signal, maybe that your Bluetooth signal, or it may be LoRa, low range signal, which is exploited to shift to the other range of the Bluetooth. And sorry, I make a mistake. This is the incident signal. This incident signal, actually RFID generate this radio frequency signal, which forced or which is exploited to shift to the Bluetooth or low range signals. So if there is any Bluetooth or low range or LoRa receiver, so they receive the signals and get detected. So RFID operates in the concept of a symbiotic radio, and that's called bistatic device. Symbiotic radio. Apart from that, there are ambient backscattered communication. Ambient backscattered communication means instead of simply a single generator or RF signal source, it could be the existing or ambient RF signal. This existing ambient RF signal may be your cellular communication signal, or it can be your Wi-Fi signal. So careful about what I am going to say is that this can be a dedicated oscillator circuit which generates only sinusoidal carrier signal, like this representation says, or it can be bistatic mode of this, which is generally used in the RFID. Dedicated signal source is used, or it can be the ambient RF signals, that is cellular communication, or it can be your Wi-Fi signals. Now, what is the limitation here? Only one or two antenna is used. That is why the backscattered signals, that is reflected path signals, are also very weak. Why? Because you can see there is one wireless channel, there is another wireless channel. So two-way path loss, heading channel or at loss. So two-way path loss, this limits the quality of the received signal of the IoT devices. So low data rate transmission. And at the same time, improvement of the primary communication is also not much. So that is the limitation in the conventional backscatter communication, because there are only one or two antennas used in the backscatter devices. So MIMO benefits, spatial diversity benefits, spatial multiplexing benefits that we achieve or that we can obtain in the context of MIMO, that is not there. On the other hand, because of the two path loss, the signal quality in the reflected path are also not up to the mark. So remember, what I am going to say is that it is an existing RF sources that generates the RF carrier. This impinges on the backscatter device. Backscatter device use one or two antenna. In fact, periodically, now you may say how it communicates its data. Let's say there is a passive device. That passive device captures the data and it likes to communicate to its receiver by means of your, what I'm going to say, by means of digital communication. So this data represented in the form of a symbol. Now what it is done? Now periodically the load of this backscatter is changed, and as the load change, as you know, are of electronics background, if you are, you know, as the load changes, then your reflection coefficient changes. And so symbols mapping to the load, mapping to the reflection coefficient. Now at the receiver, by detecting this reflection coefficient, the corresponding symbols are. But the traditional backscatter communication, the problem is what? One or two antenna is used in the backscatter transmitter. So the diversity benefits of MIMO is not gained. That's the replacement is by RIS, that is reconfigurable intelligent service. Okay, so backscatter communication, symbiotic radio, as I say, backscatter is a cooperative communications for simultaneously supporting the passive IoT communications and primary communication. This leads to the symbiotic radio, the term that comes from the biology, the symbiosis, right? So primary communication, primary signal has its own RF carriers that take care of its own data transmission. That carriers now being used by the passive IoT devices, the smart devices, whichever captures data, that data impinged onto the shoulders of the primary carrier signals and being transmitted. So in big scatter device, primary communication shares the same radio frequency signal, and even the receiver. I will show you there are two modes of receiver. Here it is a cooperative receiver, single receiver. That means primary communication not only share its radio wave carrier but also its receiver. Somewhere it can be different. Two different users. That means the primary communication has a primary its own primary user receiver, and backscatter device has its own receiver. So it may be separate receiver for primary communication and IoT devices, or it can be common or the single receiver, which is called cooperative receiver architecture. So we will see later that there are two different architecture, receiver architecture, which possible in case of your symbiotic radio. One is the cooperative receiver architecture, other one is the separate receiver architecture. We will definitely see in the context that separate receiver architecture is difficult because you have to consider two overhead, two receiver, two set of wireless channel estimation, and overhead is also more. And beamforming is also become very stringent. I will come to this point, and that will be clear in the figure. So we that SR device, or the symbiotic radio device, is designed to join it. Let us again back to this. So in this case, how the receiver operates? Now this is the direct signal, and this is the direct and passive device signal. So the receiver receives both the primary communication signal and IoT device signal. Now primary device communication signal is first extracted or detected, and from the composite received signal, this interfering effect is cancelled, and secondary receiver gets back the backscattered, the IoT device data. So what I'm going to say, a kind of interference cancellation by means of multi-user detection is done. Here is primary signal direct path, and in this path primary signals and backscattered composite signals come to the receiver. Receivers are getting both primary communication signal as well as passive IoT device signal. Now it first detect the primary signal considering backscatter signal as an interference. Once the primary communication signal is detected from the composite signal, its interfering effect is cancelled and it left with the passive communication. So that's basically the concept, right? As if x plus y, an estimate of x is obtained, then from the x plus y minus the x estimate, it gives rise to the y estimate. Y estimate is the passive communication or passive communication data for the receiver. So BS links use transmit IoT data and also improve communication. Backscatter communication leads to the symbiotic radio concept, as I say, but power of backscatter link is much smaller than the direct link. because there are two path loss, two link path loss, not much improvement in primary communications. That means whatever primary communication in the direct path was there, we were expecting that as this direct path due to fading is not up to the mark, we are thinking that this reverse, I mean the reflected path would also be augmented, but because of the two loss, two fading, so it may not be up to the mark. So that because only one or two antenna is used. The scenario can be drastically changed if we have a scope of multiple antenna or multiple reflecting element. That is basically the RIS. I'm coming to this part. So power of BS link is much smaller than that direct link, not much improvement in primary communication, and low data rate for IoT. Here is comes RIS. So one or two antenna problem or the diversity gain benefits which was impossible to get in the conventional backscatter communication is now being achieved through the RIS, reconfigurable intelligence service. What is a RIS? You can think of like in camera systems as if in a CCD sensor, when you capture photograph, there are two-dimensional array of photo sites. When a scene or when a light impinge on it, it capture the photo site. Each photo site capture the I mean photons or electrons like that. So same thing here in reconfigurable intelligence surface. It's sort of things like passive reflector. It's sort of like passive relay. Now I take help of an example. Basically, it plays the role of a relay or it plays the role of a reflector. Now, you know that in any long distance communications, there are relay. This relay may be amplify forward relay. This may be decode and forward relay. This may be compress and forward relay. But all these relays are active relay, active device. Whenever there is active device, energy consumption and power consumption is equal. If it would have been a passive device, you know, let's now come to the outside the scope of the communication. Or sometimes we say wall. The wall has also ER. Particularly, for example, I take an example. You might have, I don't know whether you have an experience or not. Let's say, for example, if there is a couple and someday, like say, for example, because of some reasons, if the couple do not communicate each other. So if there is a small kid at home, generally one say others. You tell your mothers or you tell your fathers to do this one and that one like that. So sometimes this, that the kid or say, I will not be able to say. If you have to say, you tell like that. So it's sort of things like relay. The kids becomes a relay, which the communication between parents who are having some problems of direct communications, and this active device, the kids response are the way. But if it were not kids were there, sometimes the one can communicate. This has to bring, that has to bring, like that. It's sort of things say, wall achieve like play the role of a reflector or play the role of a relay. So this is a passive reflector. Like the wall is a passive reflector, unlike the case of key, which is an active relay. Here is the RIS. So you can think of that RIS is a two-dimensional array of tiny mirror or tiny antenna elements. So whenever an electromagnetic wave impinge on this set of array of tiny mirror or antenna, we would have multiple copies of the reflected wave. Remember that diversity gain of MIMO that we are getting. So a radio wave, a single radio wave, impinge on the multiple tiny elements. I can go to the slides first. Let's say, yes. So this is, for example, so this is an array, two-dimensional array of this mirror or an antenna, which acts as a passive reflector. So a radio wave impinge on each, and when reflected, we do have multiple copies of this vector. And these multiple copies of the vector, if we make them in line, I mean make them in phase, the resultant vector will be large. And if the vectors reach the receiver with out of phase, the resultant vector will be small. So that can give rise to, so the impinged radio wave, when it reflects by the tiny reflectors, if the phase we can control in such a way that the reflected vectors reach the receiver in phase, then we can create a strong signal. And if the reflected multiple copies of the signals reach in out of phase, so weak signal will be there. So by that way, we can create a strong signal. By that way we can create a directional signal, because we can adjust the phase in such a way the signals to be in more strength in a particular direction, and other direction we can block the signal. We'll come to these issues later. So what I'd like to say is that, as if you can imagine you are having at your room, there is a wall or the rooftop or the billboards, and there are some two-dimensional array of two-dimensional array of uh, reflectors or tiny mirrors, and radio wave impinge on this. Somehow there is a control device that control the phase of the reflectors, so the multiple copies of the signals reach receiver in phase or out of phase, giving rise to signal strength and block. But it was required in the context of Alice Bob communication. Bob needs to get a good quality signal. So it is expected that the reflector give rise the multiple copies of the signals which are in phase, and Bob will get an in phase signal, good signal quality. And Eve will get a bad quality signal, because the phase should be controlled in such a way that whatever multiple copies signal reach Bob, Eve, it should have out of phase. So the blocking or the weak signal, and which I tell that we need to have a signal quality, good quality signal, bad quality signal. So favorable channel, disfavorable channel. That's the intelligent reflecting surface. Come back to this discussion first again. So what I was going to say is that reconfigurable intelligent surface, which we call as RIS, or people also can say intelligent reflecting surface, IRS, is a planar surface typically consisting of large number of passive reflecting elements to enhance wireless communication. Why it is passive? Unlike the kids, that's such an active device, active relay, who offends or who sometimes responds other way. It may not be, I mean, this example may not be agreeable to all, but of course, the active device also favorably responds or politely responds. But I just like to tell that is active device is power consuming. On the other hand, these passive reflectors, you may not have to use the power. That is my objective to talk, and that's the example I cite here. Nothing else. Control to manipulate the propagation of electromagnetic waves. What we are getting, the signal quality will be improved, coverage zone will be improved, the interference, inter-user interference will be reduced, and improving the security of the network. How? Now, if as I say, that Alice communicates, Bob is there, legitimate receiver, Ibs is there, I mean, illegal receiver. So we need to have multiple copies of the signals to Bob as well as Eve, but these multiple copies of the vector, all signals are vector. Signals are nothing but a vector. In fact, I believe on a large set of vector theory. Individual, we human being, can be thought of like a vector. You believe or not, if it is in the simple sense a vector, our ability to do some work is the magnitude, and our willingness to do is the stage. So when people say that we have a lot of problems, the country like India, because huge population, that's another problem. This is the problem. But again, the human resource is also a vector. If these resources are used properly in phase, it would be wealth. When these resources are out of phase, there are destructive opportunities. So a human being can be thought of like a vector. Human being can be thought of like a vector in the sense all our attributes, like say when in the pattern recognition problem, a human is designated as a point in the representation space. The points consist of a tuples. The points may be the height, one coordinate, other is the weight, the guard, and all these. So in either sense, or in any way you can thought of like that. So basically signals are nothing but a vector. Signals has magnitude, signal has phase. Just like the vector has magnitude and the phase. We are exploiting this in RIS to have a good signal in desired direction, to have bad signal in the undesired direction. So that is basically the RIS. Now, how does RIS work or IRS work? I already talked about that. You can think of RIS as a two-dimensional array of tiny mirrors or antennas which can be adjusted. That means so again, those who are electronics people, you know that this antenna or the mirrors or the reflector devices. So you just change the load of these devices. And once you change, when radio will impinge, so the reflection coefficient changes, which can be adjusted to change the way of wireless signals bounce to them. Now, by carefully controlling this reflection, we have the few benefits to achieve. One is that signal boosting. So weak signal. Remember, your RF signal is a single copy signal, maybe multiple copy. So from the transmitter, the single RF wave, when impinge on the two-dimensional reflectors, after reflection or remodulation, there are multiple copies. And these multiple copies may strengthen the weak signals. Focusing. If you control the phase rather than scattering the multiple signal copies of the signal, you can focus them to a particular direction. So you concentrate wireless signal in a specific direction. And other way, it can block. You can control the phase. So in such a way that in a particular direction, for example, each direction, no signal will go. So in fact, Alice Bob communication, in between, if you can think of a reflector. So if the signal from Alice goes to the reflector and from the reflected signal goes to Bob as well as Eves. Now you can adjust the phase of the reflectors, the tiny mirrors devices, such that the Bob can have a good quality signal and Eves can have a bad quality signal. So by that way, you can block the signal to the direction of the Eves. That sort of things will be. So security benefits can be achieved. Inter-user interference can be reduced. Strong signal can be generated in the rear direction. So that's all benefits we can get. Now go to the structure of the RIS. What exactly it is? I show it here. You can see this is a substrate, and it's basically which I show. So this pink color, this is the metamaterials. So metamaterials inside. So it's basically a metamaterials. What is RIS? A two-dimensional array of metamaterials. Each metamaterials contains uh, sorry, it's a reflecting element. So this is a reflecting elements. This is the metamaterials. So it's a reflecting elements, two-dimensional array of reflecting elements. This reflecting elements contains metamaterials, and this is the pin diode. Pin diode means positive intrinsic negative diode. Positive intrinsic negative diode, and this is the substrates. So what is doing there? This controller adjusts the phase of, I mean the bias voltage. Rather, I would say this controller configuration link adjusts the bias voltage of the pin device, which changes the phase angle and accordingly the reflection coefficient. So the second thing what we call it that like, so if this is the signal source impinge on this, so from the source to the RIS there is a communication link, and from the RIS to the receiver is another communication link. So channel model becomes is what? This is sort of H, the total communication channel, G transpose and HR. So that means what? It's a vector, I mean it's a matrix. So G corresponds to the channel vector or matrix from transmitter to the RIS link. H corresponds to the channel vectors from RIS to the receiver links. And phi is a diagonal matrix, diagonal reflection coefficient matrix. So here this PIN diode bias voltage is phi. So whole composite channel is the channel matrix or channel vectors from source to RIS. RIS contributes the phi term, which is nothing but your reflection coefficient matrix, and again from RIS to the receiver is the another matrix, that is H matrix. So the channel matrix. So this is the composite channel. Very difficult to model it. Very difficult to model it. Signal model is what? The reflection coefficient in RIS. So phi is the contributor. H and H, G and H, we do not have any control in that sense. But reconfiguration is possible by means of adjusting the phi. Now, diagonal matrix. So this is the contribution. Phi is the contribution of the reflector surface. So the reflection coefficient matrix, the phi can be written as alpha e to the power j theta. Alpha corresponds to 0, 1. So as you know, 0 and 1 corresponds to what? Total absorption and complete reflection. So one can play with optimization problem. Configuration of the by optimization, what I am going to actually mathematically I like to say optimization, but I should say configuration of the RIS. You need to adjust the alpha and theta value, and theta value is 0 to 2. So alpha, you can understand, it can take values of 0 to 1. By corresponding to 0 to 1, it likes to means complete absorption and total reflex. So this is the RIS. Hardware architecture, it is nothing but two-dimensional array of reflecting elements. Reflecting elements contains metamaterials, metallic metamaterials, and positive intrinsic negative device, which is controlled by this control device bias voltage, and these are fed put onto the substrate. This is put onto the dielectric. Now, I already told a few minutes back that receiver, there may be two types of symbiotic radio receiver architecture. One is the cooperative receiver architecture. You can see this is the IoT devices, the smart devices which capture data. This captured data, actually this is the backscatter device. RIS now plays the role of the backscatter device. This is the primary transmitter. You can think of it maybe Wi-Fi communication or cellular communication signal, RF signal impinge on this. Now this RIS, the IoT device, basically it impinge on its own data, passive IoT data, onto the RF carriers of the cellular communication or your Wi-Fi communication. Now there are common receiver. That receiver is basically your uh, primary receiver as well as this. What basically they do in the operation, they follow the multi-user detection. As I already say that this is the direct path communication of the primary user, and the reflected path communication contains the composite signal of the primary communication as well as the IoT or the passive communication. So the receiver, upon receiving this composite signal and from the direct path, the original signal, it cancel the interference and fever, the detect the primary communication first. Once the primary communication is detected, then it cancel out its interfering effect and detect the your, what I would say, that IoT devices. Now you may say, what is the relevance that the same user, the same receiver will be the effective for primary as well as secondary communication. Imagine the smart home. Smart home, you have a smart uh, mobile. A smartphone. At your smartphone, you have a at your smart home, you are having smartphone, and so IoT device captured the data, and their data is now coming to your smartphone, which is using the existing Wi-Fi communication. So you can get the information of the valuable information of your home, what is captured by the passive device, IoT devices. This is one structure. Other one is the separate receiver architecture. The separate receiver architecture, what it says, instead of having a single receiver, the composite or cooperative receiver, there are two different receivers. One is the primary receiver and second is the IoT receiver. Now you can see here is the interference of this one, there is the interference of this one. So what is there? The same way, the direct communication of the primary transmitter to the primary receiver, and the primary transmitter signal is also coming to the IoT receiver. Now it is the symbiotic radio communication signal. You are having these two communications. Now the definitely challenge or the complication or the complexity of the system is much more in the separate case. Why? Now you are having one channel, here is another channel. Earlier this was a single channel. You need to control the phi for this one only. Now you need to control the phi, this one as well as this one. And important things, the performance of RIS to a great extent depends on the channel state information. In mobile radio environment, channel state drastically change. Very quickly change or slowly change. that give rise to slow fading or fast fading, like that. So channel state information, estimation of the channel state information or knowledge of channel state information plays an important role, and it becomes very challenging. Overhead becomes challenging in separate receiver architecture. So there are more communication overhead in channel estimation. And second thing is passive beamforming design at RIS of it's much more difficult because you might have two receiver, two different requirements. So your phase phi need to have a conflicting requirements, or maybe very optimal set of phi value determination is very important, because it might have this channel needs one kind of requirement, this channel another requirement. So difficult to support multiple receivers. These are the relative merits and demerits of receiver architecture. Now coming to the benefits of RIS, what is the operating principles? What benefit is like to provide? So operating principle is what? The spectrum sharing. As I already said, time and again I am telling the same thing. Symbiotic radio is highly efficient spectrum because primary communication and secondary communication, two different set of data having different data sets, are being transmitted by a single carrier signal. Now you can say how it is possible. Yes, it is possible because you can make use. There are two different architecture again. One is called parasitic symbiotic radio. Other one is called commensal symbiotic radio. That means those who are teaching electrical communication, you know. So if you make equal the IoT device bit rate, I mean the data rate or symbol duration, and primary communication data rate or symbol duration same, then this will act as an interfering signal. That means in this symbiotic radio communication, if your symbol rate or bit rate or bit duration and symbol duration of these are same, then one can be thought of like an interfering signal down. On the other hand, in conventional symbiotic radio architecture, the IoT device bit duration is made larger. That means IoT device data rate is small compared to the primary user data rate. Again, I am repeating, in conventional symbiotic radio, that primary user data rate is much larger than that of the passive IoT data rate. In other sense, the duration of bit in case of uh, IoT is larger than that of this primary. So it can be thought of nothing but a multi-path rejection problem. It's a multi-path problem of same. That means IoT device signal is nothing but a multi-path signal of the primary. So in that way, several receiver architecture is possible, and design principle. Basically, the optimization of both primary and RIS. So in your primary, there are multiple antenna. We will come to the case study. Multiple antenna. So you have to go for active beamforming in the primary and passive beamforming in the RIS. It's a joint optimization problem, primary and RIS, and detection problem. So operating principle is what? Spectrum sharing, and data of passive deflecting device is modulated onto the incident RF signal transmitted. So design principle, as I said, transmission scheme of PT and deflecting device are cooperatively designed, and then information is jointly detected at the receiver side to cancel information as much as possible. Now, performance of the SR or semantic radio heavily depends on the performance of the passive reflectors, that IRS. So that is why this RIS is an ideal candidate for it. That means performance of SR heavily relies on transmission capacity of the passive device, and RIS is an ideal candidate to the passive device. Benefit is what? Full duplex passive communication, enhancement of quality of primary transmission, passive transmission to send IoT data to its desired receiver. So primary communication perspective, it's a duplex form of communication, full duplex passive form of communication, and passive transmitter to send IoT data to the desired receiver. So this is basically the principal operation of RIS. Now, what advantages we are getting? The advantages are passive device need not have to use the separate RF carrier. Only the primary carriers is used by the passive device, so it is the spectral efficient. At the same time, passive devices are not using RF circuits of its own, RF signals of its own, so no use of the power hungry the oscillator or amplifier or converter. baseband signal processing circuit, which are costly and very, power consuming. So you need not have to use that. So that's why it is power efficient or energy efficient. So no need to emit new radio for additional IoT transmission. E, that is energy efficiency. What is energy efficiency? I'm again repeating, energy efficiency is a term which is the data transmission rate divided by power consumption. The physical meaning is how efficiently a given power is used for data transmission. That means by using low power, more amount of data transmission. So EE is data transmission rate divided by power consumption. Our objective to be data rate to maximize or making large and power consumption low. So E maximization is an important thing. Baseband signal processing modules and power hungry RF chips are not needed, so power consumption is reduced. EE is improved. Control circuit design, control circuit which bias the voltage of PIN is also very difficult. Other benefits you will see, particularly in the context of application, this RIS, you can have different configuration, different shape and size, and it can be placed in the walls, it can be placed in the rooftop, it can be placed in the wall of the bus or vehicles, it can be placed in the billboards. So it should have a different shape and size, and that benefits to be available. So high spectrum efficiency, as I said, passive IoT devices need not have to use. So this is the jointly designed, optimized and detected with primary transmission. Powerful beamforming gain is increased overall AC, that is spectral efficiency, through a large number of elements in RIS. That means a number of elements plays an important role in the designs. So it becomes a cumbersome optimization problem. Remember that primary communication and secondary communication, that is IoT communication, passive form of communication, active communication and passive communication are taken together. So receiver designed to be optimized, beamforming at the primary, passive beamforming at the reflector, position of the reflector, phase shift of the reflector, reflection coefficient of the reflector. These are all design parameters you need to control based on the requirement of your applications. Will come some of these in latter part of this talk. Cost, low cost metamaterials elements. No need to expensive baseband signal processing module. So your RIS provides the spectral efficiency, no extra carrier for the IoT device, no power hungry RF circuits, so energy efficiency, different size and shapes, so it can be configured in different way, it can be placed in the respective places, maybe at the rooftop, at the corner of the room, at the wall. So all these benefits can be achieved. So this is the advantages. Now application, if we come, there are many applications, huge applications in diverse applications. There are papers, there are surveys. It's very emerging fields. Symbiotic radio and RIS people are working. Particularly, I will also go one part touch upon. Particularly, the reinforcement learning is extensively used in the framework of your RIS. And deep Q learning, particularly the DRL, is also used. I will come to this part, but before that, some of the application I'm talking about. This application, you may say it's not merely like the application I'm talking about here. The first application is the electromagnetic radio wave sensitive environment. Now, each application, based on their requirement, demands a different form of mathematical form of the problem, and your design problem will be different. I will come at the end one or two applications. Let us come to the some hospital or some laboratory, sophisticated laboratory. There are very sophisticated instruments that you need to protect from the electromagnetic radiation. What I'm going to see, you understand? Suppose you are having a hospital. In hospital, there are very sophisticated scanner and all very instruments are there, which needs to be protected from the electromagnetic radio waves. Or some lab, there are instruments which needs protection from the radio wave emission. Now, in this environment, there are lots of smart devices are there. The smart devices are continuously capturing data, and that data needs to communicate. For communication, you need to use power. If you like to communicate reliably or high data rate transmission, your power should be very high. When you go or improve your power, that will emits radiation and going against the electromagnetic wave sensitive radio devices. So there is a restriction of power limitation in such hospital or lab environment. High power communication. What to do then? So in one side, to protect the devices, to protect the instrument, power limitation would be there, radiation free. On the other hand, smart devices likes to communicate data, and for that it needs power. So what you can do? You can keep the power small, but you can put the RIS. And that RIS, as it plays the role of a many people, you can think you are having a weak voice, and your weak voice, being an able man, you are a passive active device, you are a able man, but somehow you like to restrict your voice. Now you are giving 100 or 10 child, and in fact the child has feeble voice, but 10 child, if they collaboratively convey your message, it would be a high power signal, and that's its benefit. That's the things are here. So communication of electromagnetic, hospital and laboratory sensitive to electromagnetic radiation. So here this is the requirement. On the other hand, if you see the smart cities, you have to use a huge amount of sensor, capture data. You need to monitor video monitoring. So what is the requirement if you like to design a symbiotic radio system? So if you like to design a symbiotic radio system for healthcare or for lab, your requirement is something. If you design a symbiotic radio system for smart cities, what the requirement to be smart city? The smart city requirement is what? You should have a you should have used lots of sensor, and that data needs to transmit at high data rate. You need to monitor video signal. So high data rate transmission is essential. That means outage to be low. So your tasks to be in such a way that your objective function should be data rate to be large, or outage or in data rate should be minimum. So this is very one application, right? So these are smart city infrastructure for monitoring and management. So in case of smart cities, your objective function should be high data rate transmission or low outage, and you can make use of the RIS to meet that. Now, when I come to the smart homes and smart home, then what would happen? In a home, when you go for high frequency signal, there are bricks and walls, concrete walls. The walls attenuate your electromagnetic waves. So your signal strength will be very difficult. In your indoor application, you can see sometimes you are having a very feeble weak signal. The concrete walls, particularly it would be very severe if the millimeter wave communication is used for your phone communication and telephone communication and others. Now what would happen? In that case, your concrete walls and all will attenuate the signal. So signal strength will be very small in indoor. What would happen? You can make use of RIS. You can put your reflectors to the rooftop, or you can make use at the corner of the room, and that provides a good signal strength. So when you design for a smart home, you look into considerations that attenuation will be the factors, which is an obstacle, which is a bottleneck, and you need to provide the high signal by means of taking the RIS. So this is it. Now Internet of Vehicles, another application. The car. Now car needs to communicate. So vehicle to roadside or vehicle to vehicle communication is essential. Now this for communication you need to have a carrier. What is the carrier signal? What is the spectrum? Spectrum is not having that. So what you can do, you can this information, you can put a your RIS onto the roof of the bus or onto the wall of the vehicles, and it can make use of the high reliability transmission signal, low latency. So when it is a vehicle, Internet of Vehicles communication, so vehicle to vehicle communication or vehicle to infrastructure communication, it should be low latency and high reliable communication, and that is only possible provided you have enough carrier to, the spectrum to assign the vehicles, which is not possible. So you can see here is that RIS is used, and it can provide say good signal. This is the smart cities application, this is the smart home, and this is your smart radio environment on hospital. Some of these application in particular context, healthcare, I will we have worked and we will talk about this in the later. So with this application, let us come to some of the typical application scenario. This application scenario may be anyone. I'm not specifically talking about any application initially. It's just a merely design, a D2D communication. It can be making use of the indoor communication of home communication. What is there? This is our work. CRIRS, cognitive radio IRS underlay. What we are going to do? This is the primary transmitter, this is the primary receiver, CU, and this is your device, this is transmitter, and this is another device. So this is the DTD communication. This device to device communication accomplishes low data rate, low latency communications, and there is incidentally a direct path. But still, the as I say, no, the attenuation of the particles and all, because if you are using the millimeter wave communication, the dust particle, water particles, and others also consume that signal stream. So this signal seems to be weak signal. We are in the wall we are having RIS, reconfigurable intelligent surface. So your device signal along with the direct path, there are reflected paths. Generally, in existing literature, you will find that device to device communication, maybe the obstacle is there, non-line of sight path, so direct path is not there. But we consider the challenge here is we consider in device to device communication the direct path as well as the RIS reflected path. Our objective here is to place this RIS, where to place, and to control the power such that the signal to noise ratio is maximized, SINR is maximized. So you can think of here that this is the primary communication, primary transmitter, primary receiver. Now CU corresponds to the primary receiver, cellular receiver, and this is the base station, that is the cellular communication. Now this communication interfere the receiver of the device. So you can think of it as a IoT device. IoT device. So IoT device is receiver. U stands for here receiver, and A stands for transmitter. So it is the IoT device whose intention to communicate to data to the IoT receiver. Along with this direct path, it also makes use of RIS. But since there is over the same carrier frequency or spectrum, the primary communication is going on, primary signal appears here as an interface. And at the same time, the secondary communication or IoT communication also appears in the form of interface to the primary receiver. So we are going to SINR calculation and maximization. So but our objective is SINR calculation for this communication, device to device communication only, because the paper is RIS reflection and placement of optimization for underlay D2D communication. That means as if we are only bothering about the IoT communication. IoT communication is using primary spectrum, so we need to protect primary. That means our power of the device should not exceed such that interference in this path will objectionable to this communication. So that is our constraint. This constraint, C1 constraint, is the interference protection. That means the power of the device should not in such a way that the interference of the PS primary exceeds this limit. So it must be restricted with this. And here is SINR. This SINR is the signal to interference ratio for this communication, D2D communication. While it considers its own power in the form of signal, it also experiences interference of the primary transmitter. So that's why we are considering SINR. Our objective, the design variable is we like to maximize SINR, because if I maximize SINR, data rate to be maximized. And what is the design variable? The parameters. One is the power of the device, this is P, and D, where to place. We are considering the parallel. That means will it be placed here, or will it be placed here, will it be placed here. So this is along this line, only along this line, this is parallel to the DS, where to place. So the D is the place position of the RIS. So this is the constraint optimization problem. SINR maximization is objective, the design variable is the power of the device, position of the RIS. Constraint is that the device power will not be objectionable in the form of interference to the primary receiver. This is that condition. Power is non-negative, so that's why this is better than this. It should protect the power should, I mean, device should also be maximum power limited, because IoT device should have a limited power. So this condition is this one. That means you should not exceed, you should not use the maximum power in that way that its lifespan will be. I mean, you should not operate it exceeding a certain power, which is the limit of the power of the device. So this one, and D is the delta. That means D is the distance. It must be greater than equal to delta some position, and this is it. So these are a constraint optimization, and when we look for this, it's basically a very cumbersome optimization problem. And after certain approximation, we decouple this and we achieve these results, which gives the position D stars and the P stars. And this is our paper, which was published in the IQAC. Now, the same mathematical model has been extended. Here we are going for signal to noise ratio, interference noise ratio maximization. In other, we have outage minimization. That means a certain data rate must be always maintained. When it is not maintained, it is called outage. That means a secondary or IoT device likes to promise a certain data rate. If this data rate falls below that prescribed data rate, we call it an outage. And that outage, that means number of times the data rate transmission below the prescribed data rate, this probability should be low. That's called outage probability. And our objective is minimization of the outage probability. So in next work, the same problem, what we have done, instead of SINR maximization, here our objective will just go on other way, minimization of the outage. That means we ensure that a certain data rate, data transmission rate must be maintained. And if not maintained, there will be outage. And that outage should be minimum, subject to again the D and the placement of the RIS and the power of the device. But what interesting thing we consider here, as because a conference version has to go for a journal version, what we have done, earlier it was a parallel architecture, two different topology of the RIS placement. The topology earlier was parallel to this device to device cover. So we saw here it is this and it's a parallel. And now we explore this one in an elliptical topology. So two different topology we considered. One is the parallel, other one is this. And this paper is accepted and published. Already it is available in IEEE Transactions and Cognitive Communication in IQAC, volume 10, number 2, in 2024 it is published. So again, other requirement is same, interference protection of the primary. Remember that passive communication, win-win game. So it should have a mutual interest. Okay, you are sharing the spectrum of the primary, but your transmission should not be objectionable to the primary communication. So that's why interference protection must be maintained. This is the non-zero finite power, this is the limited power of the device, and this is your constraints for the placement of the RIS. Now, what we problem face here in such kind of problem in existing literature also, it's a very complicated, cumbersome, non-linear, non-convex optimization. Non-linear and non-convex optimization problem. Classical optimization techniques is very difficult to make. We have to make lots of approximation and get solution. Such kind of problem can be better taken care, and when there is a dynamic environment, because the mobility in the primary transmitter is varied, and there is feeding channel, obstacle, and all these. So whole communication channels are very stochastic or random environment. So it makes this optimization problem even cumbersome, even difficult. So that's why the reinforcement learning, a kind of deep learning algorithms, a kind of machine learning algorithms is also used. I hope you are familiar with different types of learning techniques: supervised learning, unsupervised learning, and reinforcement learning. Supervised is basically your supervisors are there, ground truth or level data is there, train the model and predict or classify like that way. Unsupervised, you do not have the any supervisor or like that. So one is the data driven Other one is the task driven. Reinforcement learning is a kind of learning. The way we generally learn by mistakes from the experience. So if you have an optimization problem, and optimization problems are sequential, or a task assignment is sequential, so your optimization problem depends on the states. So it's basically a sequential problem. You can make use of the reinforcement learning. So reinforcement learning is a kind of unsupervised learning where an agent interact with an unknown environment, and by virtue of its interaction it gains experience. It either rewarded or it gets penalty. So an agent in an unknown environment interacts, it takes some actions, the actions gives out some reward or punishment. At the end, agent should have an objective of cumulative reward maximum. So that's reinforcement learning. Now, reinforcement learning, when used for solving this non-convex non-optimization problem in some of the RIS problem in the existing literature, and I will be coming to that. Before that, I will just briefly discuss about the reinforcement learning, which I have already introduced. So, supervised learning is task-driven, predict next value. Unsupervised learning is data-driven, identify clusters. Reinforcement learning, reinforcement by history. You can understand here that this is the gentleman. Here is one hand, there is another hand. This is a puppy. This he does not know what to waiting for it. Either some food or like some, sticks. So it may have its action, and the action give rise to either rewards in terms of some foods or in terms of some participants. So maybe that. So basically, it's I already say reinforcement learning in machine learning scheme where agent interact with an unknown environment, takes action, get feedback from the reward or punishments, deploy policy. Develop policy so that the cumulative reward to be maximized. Notion of cumulative reward to be maximized. Basically, RL involves four things. One is the optimization. Second one is your sequential. But I would say that the immediate actions reward is not. It should be emphasized after some times, and then your exploration and generalization. So an RL involves four things: optimization. Goal is to take certain actions such that you should get optimal value. In the sense, the reward should be maximum. Delayed consequence. That when you take some action, you don't expect that outcome would be envisaged right at this time. It might have some impact in the latter part. So the delayed consequence, yielding the delayed consequence. Exploration. Exploration means you adapt. The agent should adapt all possible types of the state actions, and so that it should enrich the knowledge maximum. Exploration and exploitation, two things are very important in the context of your RL algorithm. Exploitation like to means whatever knowledge is having agent, you try to heighten that knowledge. Whereas exploitation like to means explore all possible state actions and go for the reward of maximization. Generalization like to means what? That agent trained, but it's learned experience to be used in an unknown situation which has not been a priority. The agent has not been trained. So finding so this is the typical optimization techniques for others. So generalization likes to means an agent should be trained in such a way that its achieved results or gain results can be used in some situation or environment which has not been experienced by the agent beforehand. So this is the structure of RL. I'm not going to talk about individual, so I skip that one. But I give you the feelings of optimization. So delayed sequence optimization depends on a particular states, some actions. The action has current reward value. It has long-term reward value, that is with a discount factor. So gamma plays the role of a discount factor which numerical values from the 0 to 1. Large gamma value corresponds to the exploitation, smaller gamma value corresponds to the, sorry, I make a mistake. Gamma large value corresponds to the exploration, gamma small value corresponds to the exploitation, and a generalization. So these four things, if you have, you can explore that RL algorithms for solution. Now, how RL can use in RIS to optimize the control. So basically, this discrete phase and position, it's very difficult to get the optimal set of values by means of classical techniques. Here you can make use this non-convex, non-linear nature of the problem can be taken care by means of using the reinforcement learning. So to optimize the configuration and control of the reflecting elements in the surface, by employing RL techniques, reinforcement techniques, IRS can adaptively adjust, and IRS can adaptively adjust the phase and amplitude of its elements to enhance the wireless communication. So this complex problem of optimization, RL can be used to solve. So it is channel optimization, signal focusing, interference mitigation, energy efficiency, security enhancement, adaptive beamforming. All these are can be make use in their possible 6G communication or in the context. You can go to a weak, strong signal. You can look for a focusing of signal in a particular direction. You can block the signal in the undesired direction. You should go for an energy efficiency, security enhancement, etc. Now, come to the typical problem where RL is used. We have also one work using RL, the spectral prediction. I forgot to include that one, but it was not using RIA, so that's why I didn't include. So the existing literature, RL algorithm is used, and how it is used, RIS enhancement in D2D communication. So it's basically a communication of cellular communication, and it's the it's a device to device, I mean the IoT device communication, and it's cellular communication. There are K numbers. So what we are going for, as in the previous example of our own, what we are going for, the outage or SINR of the device we are restricted. What they have considered here, they are considering the R, the data rate, maximize the data rate. The data rate is R what? Now sum of the data rate of the passive device as well as the active device. So this R has two components. One is the data rate of the passive device or IoT device. Other is the data rate of the cellular communications or the primary communication. So that to be maximized. Under the condition, under the condition what? Now the signal to noise ratio. That means in other way, the data rate of the device and data rate of the primary communication or cellular communication must maintain individual rate constant. That means we are going joint maximization of the data rate of the primary and IoT device, but it should not be like that, that individual interest must also be maintained. But if we do not use this constraint, going for this maximization, which is sum of this data and this data, need not necessarily maintain that it can take care of the fairness of both this one and this one. To add the fairness aspects, the data rate, and that data rate is achieved through the signal to noise ratio. So signal to noise ratio of the ith device to device pair. There are multiple device to device pair. There are multiple device to primary communication pair. So the ith device should maintain a certain signal to noise ratio, minimum ratio, and a particular cellular user must maintain a certain data rate. And this is the phase of this, and this is the position. So position of the RIS and phase of the RIS are the design variable. In our case, we were looking for the power of the device and the position of the device RIS. Now they consider this is a problem where theta, the phase of the RIS, is the design variable, and the position of the RIS is the design variable. This problem they have make use by means of deep Q learning, where they make use of the convolutional neural network. So reconfigurable intelligent surface enhanced device communication. What they have done, generally DQN is what? Now reinforcement learning and deep learning. So DQN combines here. Actually, if it is DN, they have used CNN, but DQN actually RL, the reinforcement learning, and deep learning. Particularly those who are having this DRL, there are many algorithms where DRL is used. For example, self-driving car. Whenever a car come to a junction, self-driving car, I mean driverless car, it does not know that whether the pedestrian people will come to this side or other vehicle will come to this side or like. So a CNN-like structure is used to visualize all data, extract the features after coming to this. But what decision to be taken, that is governed by the reinforcement learning. So a convolutional neural network and deep learning and involvement of reinforcement learning, or rather deep learning and reinforcement learning combined together give rise to deep reinforcement learning. In deep reinforcement learning, sometimes reinforcement learning is used for decision making, and deep learning is used for extraction of features. Here what they have done, generally you are having the complex problem of discrete phase and position. So you need to find out the large set of value of position of RIS and phase, because the size of the RIS, the tiny devices, I mean the mirrors or the elements go on increasing, so the value will be. So it's a grid-like structure. In one row you would have the device position, and in other you can have the phase of this, and a large set of design variable to find. It's a complicated optimization problem. What you can do, you can make use of a convolution, you can make use of the normal neural network. Then in that case what would happen, last layer should be your flattened layer. When it is used flattened layer, that means large set of parameters you need to train. Rather than that, what they have done, instead of using the ANN or deep neural network, they have used a particular structure of CNN. As you know, CNN has the benefits of weight sharing, so it uses the parameters, training parameters. So basically deep Q learning is nothing but DL and RL. Now if it is the normal DL, I mean the deep neural network, you should have a last stage, the all possible connection, large number of parameters. What they have done, to reduce the computational complexity, in place of that, they have used the convolution neural network and exploit the weight sharing, and that's why it reduces the computational complexity. So it's basically RIS enhanced due to the communication. The loss functions, I mean, they have used basically the reward in the form of a penalty and beta rate in the form of a reward and penalty. So this is the situation, and some of the results you can find here, that number of iterations, when the number of iterations value go on saturated. So this is the basically the random phase Q learning, then deep Q learning separately, and CNN deep Q learning. So this is that. So average reward, but this is your. So this is their structure and this given. And you can see that sum rate, that e to the power, you should have a structure like this. You can find that with the increase of the power, this go on decreasing and then again go on increasing, because with some values, so without RIS, there are the defined CNN Q learning, and you could get this value. Right? Another work, so I'm skipping this sum rate as a part of cellular transmit power, number of elements in. So this is the results for different configuration without RIS, random, Q learning, CNN plus. Now I go to the next one. This is another work where the security aspects is used. It's a very interesting work, and again reinforcement learning is used, securing channel. This is the cellular communication. There are multiple antenna, and this is the RIS. So there are device pair and there are eavesdropper. So you need to provide. So these are red marked are eavesdropper. So there are eavesdropper, and this is the secondary or IoT device. So this corresponds to IoT device, and this corresponds to base station. So our objective here, rather what they have done here in this work, This was a nice paper published in IEEE Transactions on Wireless Communication. What they have done, this is called beamforming, MIMO benefits. But here it is active antennas, so it is active beamforming. Here it is passive beamforming. So jointly optimize the active beamforming and passive beamforming. What is the objective? Objective is the secrecy, that impedance of eavesdropper, how this phase of the reflector will be adjusted in such a way that the data in the blue channel should be secure. So that's why kth user data rate, secrecy data rate, the minimum. So what this mathematics like to imply is, you see what it says, there are multiple IoT devices. Let's say kth IoT device is this. Kth IoT device secrecy data rate. Secrecy data rate means what? The main channel data rate and eavesdropper channel data. Let's say this is kth data, kth user. So this is the kth user capacity. And during this communication, what is the data it is getting? So this difference is the secrecy rate. So kth user is the secrecy rate. Let's say among this, the minimum secrecy rate should be maximized. So any arbitrary IoT device, among them who is the minimum, whose secrecy rate is minimum, now you go for maximize that minimum secrecy. That's an objective. It's a max-min problem. It's complex optimization problem. Classical approach very cumbersome, and they have used the RLM. Constant is what? The kth user secrecy must maintain a minimum limit. This is the beamforming, that is the antenna beamforming. This is so this V and V is the power. So this is the active antenna power. So V and V is the power channel matrix, and phi is this. So V is the antenna powers, the active beamforming responsible. Psi is the set of angle for the passive beamforming. So it's a design variable is the active beamforming and passive beamforming under the condition of this. This is the power limit. What we have shown, the maximum power. So this is the transpose of V and V, and this is the condition. So this is a very nice paper, and I like to take this example that how reinforcement learning, if you like to use the classical optimization techniques to resolve this optimization, constant optimization, you could not find this very tractable solution. So they have make use of this one by means of reinforcement learning and get the. Then energy harvesting, I will quickly finish up. This is one of our work. We in some this work, what we have done, the energy harvesting in cooperative spectral sensing. There were two modes of operation energy harvesting. One is the power splitting and time switching. In our previous work in IEEE wireless communication, let us, I say already in the previous sections, I mean the first talk. So that's sensing reliability to be maintained. So in wireless no, so that was IEEE communication. This is a separate paper, IEEE wireless communication paper. It's only take care of the sensing other than the data transmission. So in TS and PS mode of sensing reliability, so our objective is sensing reliability under the constant PD and this. So residual energy maximization, residual harvesting energy maximization in TS and PS mode under the sensing reliability constraints. And this work currently we have extended in the framework of an RIS. And we include a primary user emulation attack who falsify the sensing results. So we first address this work in the frame of problem formulation, like so residual energy maximization. These are residual energy maximization for power splitting and time switching. You can see the subscript PS and TS under the constraint of this sensing reliability and energy causality. This corresponds to what? Everything should be done. There should not be separate power. There should not be any battery backup battery. So secondary device or IoT device harvested energy in daylight or RF energy, and whatever it harvests, you will use that much energy. So this condition to say full causality, energy causality, like means the harvested energy is the only energy for doing all these jobs. That means after meeting this is the whatever residual energy that we should be maximized, and this is the outcome. So here again, like our RIS placement, we consider only the issues. Now the work has been extended in other work, which is the parallel mode of placement of the RIS near far problems. So this is the primary user, this is the secondary user. So in between distance like that. So this is one set of findings that we don't expect that RIS to be simply put in the middle of PU and this. This is the middle place. But when we see the peak value is coming somewhere here before 2, so it's not exactly the mid value that RIS to be placed between PU and AC. It can be that zero point 0.5 to 3.5 you there should, I mean, from here only the power is going down, here also from, so somewhere you can get the maximum value here. So this is one work. And like our electrical placement, here we consider that if PUEA is also playing the role of energy harvesting, because the JEMA or the primary user's emulation, who also radiates electromagnetic wave, misbehaving like a primary user, emulate like a primary user. What primary user emulation attack? That to falsify secondary sensing results, somebody, I mean, like a PU, emulate or radiate the signal so that it misleads, as if the primary is transmitting, but primary is not actually transmitting. So to mislead the spectrum information, often a attacker or a security threats of spectral sensing is there. Generally, primary user emulation attack, spectral sensing, data falsification attack. There are different attacks. I just consider the primary user emulation attack. But this may be the destructive concept. But again, as because it is a primary user emulation attack, it radiates electromagnetic wave. And why this radio wave, like the primary user, also to be used for energy harvesting? So it's a bad thing that primary user creates a signal like primary user to mislead the sensing information, sensing results. Now secondary thinks that okay, you are misleading me, but you are radiating what? RF energy. Why don't this RF energy to be used for energy harvesting like the primary signal? So if the position of the PUEA takes difference, how it impacts on the energy harvesting, that we are discussing here. And these results is communicated in artificial transactions on green communication and networking. So this is one. I will conclude this with two applications where specific design problem. One is IoT healthcare. This is our work recently published. What we have done, it is device to device communication, it is a cellular communication. There are 3 time slots. In the first slot, what happens? This communicates, this also communicates, this communicates, and this also communicates. That means in the first time slots, the base station and user equipments communicates their data. And in the second time slot, the IoT device 1 takes the composite signals and its own signal to IoT user 2. So this is the phase 2 where IoT device or passive, it's a two-way communication for IoT device. So in the phase 2, so in the, this is the MAC phase, first phase. So this base station and this one communicate its data. IoT device is in the receive mode, receives both the IoT device. In phase 2, IoT device 1 sends the previous slot's primary user signal or primary communication signal and its own signal to the IoT device 2. And in the third phase, or rather this phase, second phase, if we consider this as the MAC phase, in the second phase, IoT device 2 transmit the composite signal of this which is received in the MAC phase and its own data transmitted for IoT device 2. So this is a typical application of home healthcare application. You can imagine that device is the patient devices like that, and this is the hospital premises or home premises. So this is the patient one device, IoT one, and IoT device is the nurse or the doctors. From this data, this just analyze and take the actions. So it's a into a wearable device and collecting physical, physiological signals at patient, remote health monitoring. Existing cellular communication is used. So security against eavesdropping is also there. So you can think of the optimization nature of the problem. the maximization of energy efficiency. This device to device energy efficiency maximization. This device to device energy efficiency maximization subject to hello আমি আমি একটা টকে রয়েছি আমি একটু পরে so this is the energy efficiency maximization of the secondary device. Tau is the time duration of each one, and power IoT device 1 and device 2 use the same power. So P1 and rho 1 and rho 2 is the power of the device, and beta, that what fraction of power is used for the primary user communication signal to send or its own signal to send. So beta and 1 minus beta plays the role of signal forwarding of the primary user signal and its own data signal. Tau is the duration and device power is rho. So this is basically the ambience. What we have to do, as I say, that operation of RIS is fully or to a great extent depend on the channel state information. How channel state can be obtained? Because channel is so fast changing. Channel state would be outdated. Now we are using that sequential data. In the second page, this device is communicating data. In the third page, I mean in this page, this device is communicating data. So this sequential data, we assume these channels are symmetric. So one can estimate from this received signal, a sequential set of data received from IoT device 1 to device 2 and vis-a-vis, that is used for your recurrent neural networks concept. That LSTM concept is used for channel state information. So we are considering E maximization D2D CRN with eavesdropping using LSTM based channel estimation. Eavesdropping is because the IoT hospital information, some security, because the patient information is always having a threat of security, some manipulation, something may be there on, so it should be protected. So energy efficiency maximization subject to outage of primary, subject to outage of secondary, I mean IoT device, and then secrecy, and this is the harvested power. So everything, that means device, IoT device, whatever power it requires for cellular communication to propagate or of its own data to other device, this to come from, all power should come from harvesting. So this is self-powering IoT device for healthcare support, which take care of the device energy efficiency, which take care of the operative mode of symbiotic radio like communication, the primary communication and device communication and secrecy. So this was a paper published in IEEE Transaction on Consumer Electronics in 2024. So recent works. Finally, I will come to the conclude. This is my last what I would like to say. I'm sorry I'm running late, maybe little. So this is another example where you can make use of the industry, not rather healthcare. Maybe healthcare or laboratory, the first one. The sophisticated device needs to be protected, or it can be thought of like a healthcare where IoT's E maximization to enhance lifetime, target data rate of SU or IoT device, target data rate constants of to protect EM radiation, so interference protection, interference mitigation of both U and SU, power constant of IoT. So we are looking for power. So this configuration is sort of things like, oh, I forget to include the configuration, the network structure. I'm sorry. There was like the structure of same our previous works, device to device communication, primary and secondary. There are RIS. So it is the power of the primary, power of the device, and F is the basically the contribution of the RIS. You can see that alpha is equal to 1, and this is basically your RIS component. So energy efficiency maximization subject to that certain data rate for secondary to maintain, certain data rate for primary communication to maintain, interference protection, this protection is required. So C3 is basically for your protections of the devices or instruments, the non-zero power, the maximum limit of the power, and this is the configuration for RIS. So this is one work we have communicated in IEEE transactions and cognitive networking. So with this, that is the outcome. We can see that's basically the power, and you can find the different power of the PP, and I mean the primary power. This is the energy efficiency value, and this is the alpha value, that is the weighted average. So this is basically typical RIS applicable to the different scenario. I outline the talk which I make, sorry, summarize of the talk. So I started RIS in IoT communication. SR talk about the cognitive radio, RIS with cognitive classical optimization, outage aspects, outage secrecy rate, RIS in physical layer security, RIS with RL we discussed, RIS with CR in the context of I mean classical optimization, RFEH in CR IoT in presence of RIS, that I also discussed, application specific scenarios, smart home, smart city, IoV. So this is the RIS advantage, EAC, cost issue, RIS feature channel model like that. So basically, in the second part of my talk, I discuss about this, and obviously in the first I have discussed elaborately about the CR, EH, and in the basically talks of the second part is RIS in IoT communication, symbiotic radio, RIS features, RIS energy efficiency, spectral efficiency, cost issue, physical layer security. Okay, thank you so much. This is some of the references included. If you have any question, so that's conclude my. First of all, I must thanks to all listening. Listening is a very, I mean, what I would say, uh, listening is really a very painful, and uh, 1.5 hour and 1.5 hour listening is really very painful, and you have uh, so enough patience. So thanks from my core of heart. I know that it was boring and bit on one-way communication, huge data transmission in one sided. But I would be happy if you have any questions or any comments. No, thanks is okay. Some Gita, Papati, thank you, sir. It's fine. Thanks is fine. But if you have any uh, points, any comments, anything which needs clarification, or your opinion, something other way than that of my one, I would be happy to accept.
Thank you so much, sir. It was so useful and valuable session. And sir, thanks a lot for staying with us. It was not absolutely boring. Thanks, sir. Thanks again, sir.
But again, it is a binary. I mean, on information theory perspective, it should be understood all or understood nothing. Maybe. I mean, if there is no question, if there is no points, so in the entropy perspective, everything is clear or nothing clear. So if everything is clear, meaning that it's fully deterministic now, and if nothing clear means uncertainty is maximum. So entropy is maximum. Anyway, if you have any question or any comment, any points, you can say. Otherwise, uh, with the permission of organizer, I can quit the meetings.
To our listeners, if you have any sort of query, the panel is now open for your questions. And sir is also here to answer any kind of query if you have regarding both his sessions from morning as well as this evening session also. So we will have another 1 or 2 minutes waiting for any kind of queries from your end. If not, we will wrap up today's session and we will again meet tomorrow at the first session sharp at 10:30. So meanwhile, if you have any query or any kind of question related to what
If
sir,
you, if you see the literature, there are lots of works going on in RIS. Particularly, you can find the literature of IEEE transaction of cognitive communication, IEEE transactions on vehicular networks, IEEE transaction on uh, mobile computing, IEEE transaction on wireless communications. You can find, and you also see that RL or machine learning are also being explored a lot. And somewhere this design, if you can look for its application specific design, particularly in the IoT, in the fieldwork of smart homes, smart cities, hospitals, agriculture, or your Internet of Vehicles. So you can design, you can uh, write project proposal to the ministry and make use of your mathematical structure of the problem, look for solution, because it's very emerging area. People are working with that. So for the literature, you can go through this journal.
Sure, sir. So I guess there are no queries from our participants' end. So, a very special thanks to you, sir, for being with us today and delivering very good insights and very informative insights in both the sessions. And, sir, also on behalf of the entire organizing team, we would like to have you with us in similar type of sessions in future as well. And it was a really good opportunity that we heard you today. So with that and with the appeal to all our participants to join tomorrow as well for our session at 10:30 on IoT in agriculture. So we would also like to request you to have to join us tomorrow as well at 10:30, and the link will be provided in the group. And apart from that, we will be providing the feedback forms for today's session. So please take out some valuable time of yours to fill up the feedback form. Thank you so much, sir, and thank
Okay,
you.
okay. Thank you from my ends to the organizer for giving me hope of delivering this lecture. Thanks all participants or the listeners remotely on online listening and bearing me over this much of time duration. And as there is a feedback, so I hope you will share me the feedback, not in full of I mean the gist, so that it can be useful. Like organizer, I'm telling, so I would share about the feedback from the participant for my lecture, so that it can be useful for me in future. We can
Sure.
thank you again, just jokes. Thank you so much for your invitation, and thanks listener, the participant for listening. Okay, bye.
Thank you so much, sir. So with that, we conclude our today's session. Tomorrow again, we will join at 10:30. Thank you so much, everyone, and goodbye for today.